Designing data and AI architectures seem straightforward until they encounter real-world infrastructure failures and unexpected production bugs. Data workflows frequently fall apart during handoffs between independent tools, revealing why orchestration is an indispensable component of infrastructure.
That we focused on this is because it's probably the most hated point in the stack, number one. And number two, because very few people set out to deal with this problem. This is a problem that you learn that you have. This is a problem that you learn because tool A sends data to tool B, and somewhere in the middle it gets lost, or somewhere in the middle a node crashes. It's an ugly word. It's a difficult word. Most people, you say orchestration, they're not even sure what you mean. And so when instead we talk about
Orchestration may be an unappealing or misunderstood concept, but it is the literal glue preventing critical operational nodes from crashing. Distributed architectures bring the classic fallacies of computing straight to the forefront of everyday application development.
The trouble with distributed systems took us until chapter 8, I guess, to start talking about that. It's funny because the whole book could just be titled "The Trouble with Distributed Systems."
For sure.
Chapter 9, consistency and consensus, and chapter 10, batch processing. And chapter 10 is the first part of part 3, which is derived.
Dealing with the erratic nature of network infrastructure remains a foundational challenge for modern engineering teams. Applying physical engineering rigor to digital architecture helps identify structural design flaws long before systems go live.
When I think building science consulting, for many, many years, all I understood was there were companies out there that did investigations of building problems, and usually that was associated with some litigation, right? You know, you got a problem with a house, it's a leak, it's an issue of some variety. Attorneys get involved, they bring in an expert, and I think that's the misconception a lot of builders have.
Investing heavily in proactive preventative design keeps platforms running stably and prevents massive liabilities later on. Managing extensive application layers at scale has forced an engineering evolution toward dedicated platform environments.
Infrastructure more interesting because of the challenges and everything. Then I changed my field. I became a DevOps engineer at that time, and it's constantly changing. So now I think it's been transferred from the DevOps engineer to platform engineer. So now I'm platform engineer, and enjoying my life at Bolt.
Platform engineers clear the operational path, shielding application developers from complex infrastructure irregularities. Embedding artificial intelligence models directly into core operations requires structural modifications to the software workflow itself.
That's a great question. And real integration, often people think it's like adding a tool to the toolbox, maybe taking a Udemy or something on how to use AI. But it's actually patience is probably the most important thing. Unless you're even if you're on an R&D team, there's still a learning curve. There's still an adoption curve.
Successful AI deployment demands a transformation in organizational habits rather than just adding novel features. Deploying multi-intel LM systems requires robust mechanisms to handle unexpected agent failures smoothly.
Give you a sense of the complexity of the code base. It's 14,000 lines of Python. So the reason that it's complex is basically a lot of agents and a lot of fault tolerance for these agents. Every point where you insert an agent into the system, you need to handle the case that it failed. There are multiple ways to do fault tolerance. One is to ask a human, another one is to automatically retry, and then there's task-specific ways to do it. It's super dependent on the situation. But the main point is you have to have fault tolerance for every agent.
Building safety nets around individual agent processing paths preserves the overall reliability of the data pipeline. Implementing internal recycling and automated cleanup strategies yields a highly sustainable and self-contained environment.
Sandblasting, it's not so much anymore because it's very few people even use sand anymore due to the hazards of it. So it's basically like air blasting, media blasting. It's used primarily for surface preparation. On steel is probably the big one. anything that gets coated, whether it be painted, powder coated, sealed, usually gets blasted before the coating goes on to give it that profile, kind of rough up the metal.
Moving past throwaway processing architectures to reusable loops drastically optimizes data operations. Standardizing analytical dashboards on clean, descriptive templates removes excessive complexity from regular business applications.
We are on a mission to radically simplify how developers create operational dashboards. And we have been working for the last, I would say, almost a year now on a new product called Real Developer, which is really aimed at making that promise come true. We just released yesterday morning the .6.
Utilizing simple declarative configurations lets engineering teams deploy robust and fast pipelines easily. Designing cutting-edge digital infrastructure starts by mastering systems at the physical, foundational layer.
Building things from the ground up and truly understanding how they work at a very deep level has been critical. We've got an ability to control the world at a length scale that we never have before. And every time humanity has been able to miniaturize and make things at different levels, whole new industries have evolved that are just completely unpredictable. You know, the most important thing for humans is to understand things as best they can and use it for the best uses that they can.
Controlling hardware parameters at an exact atomic scale creates opportunities for completely new enterprise markets. Delivering enterprise-grade, highly regulated platforms demands tight coordination across distinct technical units.
12 years in fintech sales across student loans, SMB lending, and credit data. All heavily regulated, all incredibly complex. What makes his perspective interesting is that Lee came from law. He was a commercial attorney before making the jump to sales. And now he's running one of the most complex enterprise sales motions I've ever heard of. We're talking 10 people on Synctera's side of the deal, 10 people on the customer side, cycles that can stretch past a year, but value and deal size.
Maintaining clear technical compliance frameworks is essential to survive drawn-out enterprise procurement pipelines. Legacy transactional backbones are getting modern upgrades via seamless pipelines to cloud architectures.
Automation engineer at BMC Software, and apart from that, I do most of my mainframe community work to kind of advocate mainframe technology and share my experiences, whatever I have learned through these years. And I kind of have 15 plus years of experience now in the industry, all started from mainframe.
Building robust connections to existing mainframe environments is necessary to secure modern digital banking. Scaling complex data streams requires structured ingestion frameworks capable of executing concurrent tasks flawlessly.
About Broadway, and the title of the talk in the program is actually called Announcing Broadway, but I thought that instead of talking about Broadway and how to use it, which you can do by checking out the documentation, I think it's going to be much more interesting to talk about the road that led us to Broadway, to led to this particular open source project and how you should be able to leverage it, especially because this is kind of a long journey. We have
dropping highly customized ingestion scripts for verified concurrency models reduces codebase maintenance overhead. Storing active environmental profiles in a central hub demands multi-zone architectures optimized for localized fault protection.
Background, I have a long Unix and Linux systems administration background, and been doing that for a little over half my life. And throughout that, always a strong focus on automation. As any person here who has been a sysadmin knows that automating makes your life a whole lot easier. So as that line of work has kind of evolved now into DevOps, so I kind of put the ops in DevOps.
Automating live environmental updates allows modern applications to scale without manual service interruptions. Isolating inter-services communication into an abstraction layer helps isolate networks from microservice failures.
Today we are here to talk about how you can build resilient and fault-tolerant microservices leveraging Istio. Now, before I go into some of the details, how many people are actually using Service Mesh or Istio here? Very few. I didn't see any hands raised, in fact. So I think it will make sense to actually, go back and talk a bit about the motivation of the project, etc., what led to it.
Utilizing a specialized service mesh ensures standard path recovery, direct load distribution, and stable operation. True architectural resilience is built by intentionally injecting controlled failures into the platform to prepare for real incidents.
And I didn't get time to modify the slides, but people who are interested in high availability, the book came out on Tuesday that you should all hear about.
Designing platforms to withstand artificial internal stress builds systems that survive unpredictable production incidents. Applying targeted structural design guidelines to modern applications dramatically simplifies overall unit testing.
To be talking about the SOLID principles, which are a set of 5 design principles originally created for object-oriented programming. We'll discuss whether these principles can be applied to a functional code base or whether functional programming needs its own set of design principles. My name's Georgina, and I'm a software developer, and most of my experience has been in object-oriented Java development.
Dividing large code bases into single-focus modules guarantees systems are simpler to upgrade and review. Swapping legacy batch windows for continuous stream analytics requires processing engines with very low latency profiles.
Splunk, I am what Splunk calls a distinguished engineer. It mostly means that I'm responsible for technical direction over different slices of our product portfolio. One of the parts of that I'm responsible for is our stream processing infrastructure, which is heavily based on Apache Flink. So we're pretty heavy users of Flink within Splunk.
Stream native processing engines provide the robust transcational states needed to process enormous data flows instantly. When a platform gains traction, every accessible system behavior will eventually be integrated into someone's software.
She's now an engineering manager for cloud control planes at Google. That's in the SRE area, which is why she can give the talk that she is giving for us today. And we're very excited to hear what she has to say.
All right, thank you, Brandy. So I wanted to start this talk by asking a rhetorical question, which is, how do we know if a system is reliable?
Upgrading simple system uptime into true operational dependability is the differentiator for corporate platforms. Ensuring precise transcational state records across massive data frameworks requires tight deduplication layers.
To the final presentation of the day, I'm Amit, and Amiraj, unfortunately, is unable to join me on stage today, but what I'll be presenting here is a small part of an exciting journey that we both kind of shared together in the last couple of years. As is customary, we'll first take a commercial break. Yelp. It's all about connecting people with great local businesses. End of commercial. Let's get back to the talk.
Developing precise validation loops prevents corrupted data duplicates from breaking down downstream consumers. Executing heavy analytical workflows means distributed engines must survive individual worker dropouts over long operations.
Hello and welcome to Trina Community Broadcast 32. This is 2022 and it is going to be exciting. As you see already, we are a star-studded gang today. It's going to be amazing to talk about Project Tardigrade. And not about spore drives or like little grand animals. We'll be talking about ETL today. Before we go into that, let's see who is joining me today.
Implementing modular, task-level query retrieve paths keeps heavy cloud execution pools from failing during long computations. Decoupling storage logic from user-facing app code allows developers to deploy highly reactive serverless backends.
I'm a solutions architect with Ververica. So, we are the original
the company founded by the original creators of Apache Flink. You may also know us as Data Artisans. We rebranded at the beginning of this year, but we are the same organization. So along with supporting the open source community, we also offer some enterprise tools, so on. Flink, as its name implies, is a top-level Apache project, and we're all about doing stateful computations over data streams.
Leveraging lightweight event-driven state functions lets small architectures handle millions of daily API transactions effortlessly. Modern storage loaders must detect and adapt to incoming file layout modifications dynamically without failing.
So the first step in any sort of data pipeline, which we can see here from like a 10,000-foot view, is data ingestion. And here what we can see is what we want to do is take these input files, which can contain unstructured or semi-structured data, and put them into cloud storage. So let's say an S3 bucket, like our logs bucket here.
Using real-time directory event streams bypasses resource-intensive scanning operations over large storage layers. Achieving complete system consensus across distinct cluster environments without altering code is the pinnacle of infrastructure design.
This is the session on distributed systems, and the first talk in the session is going to be given by Ray, who's going to talk about a turnkey way to implement Paxos replication.
Thank you, Marcos, for the introduction. Hello, my name is Ray Gu from Columbia University. Today, I'm going to talk about our state machine replication system, Crane.
Intercepting network requests directly at the socket level makes distributed state replication invisible to developers. We do not write deep infrastructure safety management plans for when everything operates perfectly. We build them for the eventual breakdown.
If something going wrong, then what we've actually built is an insurance product, because that is how insurance works.
And by the way,
And so
the probability of something going wrong is 1.
it's one. And somewhere in the infrastructure, it's one. But you know this. I don't have to tell you this. Good luck trying to convince somebody of that, right?
Right.
Not only is the probability 1, but the probability is probably 1. In all honesty, it's probably no one person's fault, right?
Because large distributed environments guarantee a statistical certainty of hardware failure, orchestration serves as your primary operational safety net. Overseeing highly intricate, stateful cloud transactions can often feel like managing an exhausting, endless physical challenge.
This book is dense, and I'll tell you that I am holding on for dear life. I'm loving it. I mean, it's like I'm in a CrossFit class, and I'm doing, overhead press and, a bunch of burpees or something. That's what my mental gymnastics are going through. Yeah, this was an interesting one. We didn't get a clean cut across parts, and so there's a little shift in tone.
Maintaining strict state machine synchronization across a synchronous network calls demands total engineering discipline. Enforcing real physical separation between computing sectors stops localized hardware malfunctions from threatening whole availability zones.
World is about, and what we're about ourselves at RDH, is environmental separation was the primary starting point.
Yep.
What do you build? How do you bring this to life using the laws of physics and nature?
Yep.
In order that you don't have hot water type issues. And you're right, it was often thought about, you call when you get in trouble.
Aligning logical isolation rules with tangible physical safety layouts creates highly resilient enterprise systems. Threat vectors have pivoted from attacking secure server layers to polluting upstream third-party package ecosystems.
Evolving over the past, 10-ish years, where attackers shift their attention away from direct attacks, and they try to attack your supply chain instead, where they will maybe mess with dependencies that you include or other parts of the software. We all have seen these, like...
Locking down package registry mirrors keeps open source software security failures out of production systems. Scaling operational throughput relies on integrating advanced automation engines directly into core business processes.
AI and you actually use it every day.
Aligning platform loops with high-level corpora, a Tokay or S-grants engineering teams the autonomy to iterate it safely. Swapping manual text prompts for declarative optimization layers brings standard query efficiency to large language models.
DocETL is a declarative framework for building and optimizing LLM-powered data processing pipelines. So that's a lot of words. I'm going to illustrate this with an example use case here actually at Berkeley. So there's a big project going on that's interdisciplinary, spanning the lab that I'm part of, the EPIC lab, the Berkeley School of Journalism.
Programmatracolite tuning foundational model input structures unpredictable text pipelines into stable, fault-tolerant enterprise operations. Building closed-loop reclamation environments minimizes data, asset waste, and keeps operational costs predictable.
Has a recovery system. So once you go in those contained environments like a cabinet, you're reusing that blast media over and over. Yep. So the media gets sucked out of the bottom of the cabinet, goes up into a reclaimer, which cleans it, and then dumps it back into that blast machine. So it's like a continuous loop that you can just keep blasting and blasting with that material.
Interesting. Yep.
And then we also make blast rooms, which are basically the same principle as the cabinet.
Creating automated resource cleanup pathways allows complex cloud setups to operate sustainably over extended periods. Resiliency is not an afterthought, it is a core engineering requirement. From foundational consents, us algorithms to massive distributed runtimes, our systems must be designed to withstand real-world chaos.